Hello, this is Miss Moore, and today during chemistry we're going to discuss average atomic mass. Today's essential question: how is average atomic mass calculated? For today's lecture, make sure you have both your periodic table and your calculators available. Okay, here we go. All right, let's learn how to calculate average atomic mass, or how scientists did it, and we'll learn how to do it too. Let me start by saying this sounds really complicated. It sounds really tricky. And the truth is, it's really not. Okay, so, if you start to stress out listening to this, just relax. It's not nearly as bad as it sounds. All right, here we go. The atomic mass is the average mass of the isotopes and is based on the percent abundance of each isotope. So how many carbon atoms in the world have 6 neutrons versus how many have 5 neutrons, 7 neutrons, whatever. Percent abundance is the relative amount of that isotope found in nature. So to calculate the atomic mass of an element, multiply the mass of each isotope. And you would find that by knowing how many protons and neutrons it had, by its relative natural abundance, expressed as a decimal, and then add the products. All right, that may sound super complicated, but it completely is not. All right, get your calculators handy. We are going to now calculate average atomic mass. It's not nearly as bad as it sounds. So let's read over the question. I want to discuss a few things with you, and then we'll set up the problem. So our question says, copper has 2 isotopes, copper 34 with a relative abundance of 69.1% and copper 64 with a relative abundance of 31.9%. Calculate the average atomic mass of copper. Okay, so what this is saying is that there are 2 types of copper in the world. There's copper 63, which means, remember from yesterday, that when you have a number after the symbol of the atom, that number stands for the mass of that particular atom. Okay, so copper 63. Which means it would end up having 35 neutrons because all coppers have 29 protons. So copper 63 has an abundance of 69.1%. So walking through the world, 69.1% of the coppers you encounter are going to have a mass of 63, or they're going to have 34 protons. 34 electrons. Okay, and then we have another type of copper, which is copper 64. It still has 29 protons, but now it has 35 neutrons. Okay, and it turns out that 31.9% of the coppers in the world are copper 64. All right, so remember, we're now going to calculate the average atomic mass. So what we do is we multiply the mass times the relative abundance, and this mass times its relative abundance, and then add the 2 answers. So I'm going to take the mass of copper 63, which is 63, and I'm going to multiply that by 69.1% written as a decimal. And remember, when you have a percent and you want to write it as a decimal, you move the decimal back 2 places. So it's 63 times 0.691. And we're going to add to that the mass of copper 64 times its percent written as a decimal, which is 0.319. Okay, so now let's do the stuff in the parentheses first. Please double check me on your calculator. Make sure I'm not making a mistake. Okay, so I got for 63 times 0.691, I got an answer of 43.533. And when I do this one, 64 times 0.319, I get an answer of 20.416. All right, so now to finish this problem, what we need to do is just add our 2 answers. And I got an answer of 63.949 AMU. Remember, mass is in AMU. So now we've got to go back, and look at those pesky sig figs. And it looks to me, in this case, because, we'll do it. We have 4 different numbers there. It looks like our least number of sig figs is 63. So our final answer will be 64 AMU. All right, let's try another one. But first I want to point out that sometimes you'll be given an exact mass for the isotope. Okay, and in this case, use that mass when doing calculations because these numbers were experimentally derived, so they're very, very precise. All right, so let's try one like that. So now we have copper that has 2 isotopes. We've got copper 63 with a relative abundance of 69.1%, but now they know the exact mass of this copper 63, which is actually 62.93. So we're going to use that number instead of the copper 63. All right, and we have copper 64 with a relative abundance of 31.9% and a mass of 64.93. So we're going to use, since we know the exact mass, we're not going to use this 64, we're going to use the 64.93. All right, so now, why don't you hit pause? Try to do this without me and see how you do. Okay, so now what we're going to do is we're going to take the mass of the yellow one, copper 63, and multiply that by the relative abundance written as a decimal. And we'll add that to the mass of copper 64, the exact mass, and multiply that by its relative abundance written as a decimal. All right, so when I multiplied the stuff for copper 63, I got 43.4846. And when I did the multiplication for copper 64, I got 20.71267. And when I added them together, I got 64.1973. And let's look at our sig figs. We have 3, 4, 3, 4. So it looks like we're going to have 3 sig figs. So we'll end up with 64.2 AMU. All right, that's it for today, folks. See you tomorrow.